Hello dear students, welcome back to the tetrahedron chemistry classes. So dear students, in today's class we will see what is the Beckmann's rearrangement and how we can write the mechanism of the particular kind of the reaction, and then we will see the various applications of these reactions as well, right? This reaction is particularly important for your JEE examinations, also equally important in the NEET examination as well as for the CSIR NET and the GATE examinations, and also in various universities. This Beckmann rearrangement is a very important reaction for the BSc as well as the MSc students, especially for the BSc students, right? So without wasting too much of time, let's get started. What actually I am trying to explain today. Okay, so this is your Beckmann's rearrangement which I have written here, and this reaction generally was discovered by the German chemist, and the name of the chemist is the Ernst Otto Beckmann, right? And basically this reaction involves the conversion of the ketoenzymes to N-substituted amides, where we will use the acid catalyst in the reaction. The second point, right? It is very important. See, in your class 12th you must have learnt about the nucleophilic addition reaction, where you reacted your carbonyl compounds, especially your aldehydes and the ketones, to the ammonia derivatives, right? Like if you react your ketone or the aldehyde to hydroxylamine, then it will convert into the aldooxymes and the ketoenzymes. So basically this Beckmann rearrangements generally converts your ketoenzymes into the N-substituted amides, right? And the various kinds of the important catalyst, acid catalyst, are used in this reaction, and the most common one and the generally used catalyst is the concentrated sulfuric acid. So I can write the formula as well. This is concentrated sulfuric acid, right? Then you can use the formic acid as well, HCOOH. Then you can take the boron trifluoride, Lewis acid you can take in this reaction, again a very important reagent. And then liquid sulfur dioxide can also be used in this reaction. Then thionyl chloride, another very important reagent, SOCl2, it is also used. Then your phenyl sulfonic acid, right, where you will have your C6H5SO3H, right? This is phenyl sulfonic acid. This can also be used in this reaction. Sulfur trioxide can also be used in this reaction. And phosphorus pentachloride, right? I am not sure it is yes, phosphorus pentachloride, right? PCl5. It can also be used. Silica gel can also be used in this particular reaction. Silica gel is the very important material in the column chromatography, and also very important in the thin layer chromatography. But in the column chromatography and in the thin layer chromatography, we use the different kinds of the silica gel. But that silica gel can also be used in this Beckmann rearrangement as well. Phosphorus pentaoxide, P2O5, another very important reagent for this reaction. Then methane sulfonic acid, that is CH3 SO3H, right? This can also be used, right? And then PPA, polyphosphoric acid, another very important reagent. The very basic example is the H3PO4, phosphoric acid it is, okay? And this PPA for polyphosphoric acid is very important reagent for the Beckmann rearrangement, and the importance lies in the fact that polyphosphoric acid is the best reagent as it suppresses abnormal reaction and also resists isomerization of the oximes. See, generally when you do the Beckmann's rearrangement, there are another kinds of the parallel reactions, or say your the second order Beckmann rearrangements are also there. And if you want to suppress these abnormal reactions like your second order Beckmann rearrangement and isomerization of the oximes, then PPA is the best reagent in that case. But we will not discuss the second order Beckmann rearrangement here. For the second order Beckmann reagent, I will make a separate video if possible, right? Then the point 4 says that what about the aldooxymes? Since I have written here ketoenzymes can be converted into the N-substituted amides in the Beckmann rearrangement using acid catalyst. What about the aldooxymes? Whether these aldooxymes can also give this Beckmann rearrangement or they cannot give. right? So few aldoxymes also undergo the Beckmann's rearrangement, and a very important application where we convert the aldoxymes into the substituted amides basically is your synthesis of the isoquinolene, where cyclization would occur, right? We'll see this in the your application part. We'll see this reaction in the application part. So this is a very important feature, guys, right? Please remember this. Now let's see the reaction. What actually happens in this reaction? So let me write the reaction first. Say for example, you are having this carbon double bond nitrogen, right? And you know this OH is here. This OH is the leaving group. Please remember, this is the leaving group, and of course nitrogen would also be there. Lone pair on the nitrogen would also be there. And here I have written the pH, where pH stands for the phenyl, C6H5, and now I am writing methyl here, right? This is basically your ketoxime, right? Why ketoxime? Because it is the derivative of the ketone, right? Earlier, see how we can produce this ketoxime. For this, I can quickly write a reaction. If you remember, say this your pH. This is just for your information to brush your knowledge, right? This is methyl, and say this is ketone. This is phenyl methyl ketone, right? And when you react this phenyl methyl ketone with the ammonia derivative, which is your hydroxylamine NH2OH, then a condensation reaction would occur, right? Oxygen from the carbonyl part and 2 hydrogen from this hydroxylamine. Water will eliminate since it is a condensation reaction. Okay, it is not a nucleophilic addition reaction as I earlier said, but it is the your condensation reaction. Sorry for the earlier statement, it was not nucleophilic addition, it is the condensation reaction. Okay, and then what you will have then? You will have the pH, carbon, Me. Now you see this double bond will get a bond with this nitrogen. Okay, so when it is forming a double bond with this nitrogen, and then your OH is also there and a lone pair. So basically this is your oxime. This is your oxime, right? Ketoxime. So this is how you can produce it. So I don't need this. This is just for your understanding. So I am removing this. Okay, fine. So this is your starting material, and say you did this reaction with concentrated sulfuric acid. So I am writing H2SO4 here and concentrated CONC, concentrated I am writing here. So what will be the result in that case? The result would be quite simple. See, now you can see here this OH group is here and this phenyl and methyl are also there. Now it is a very important feature of the Beckmann's rearrangement, that is the stereospecific nature of this reaction. This reaction is stereospecific in nature, right? If you are beginner and don't know much about the stereospecific reaction, so I am giving you the link in the description box of the stereospecific reaction, and also the link is flashing at the right top corner. You can go through this link as well, right? So what is the meaning of the what is the meaning of the stereospecificity in that case, right? Since this phenyl and this methyl both can migrate to this nitrogen, but in the Beckmann's rearrangement it is found that the group which has the anti-relationship to this OH group will migrate regardless the migratory aptitude. See, in the organic chemistry there is a concept of the migratory aptitude, where some groups migrate very briskly, very fastly, others move or migrate very reluctantly, right? But here we don't care about the migratory aptitude. We only see the relationship of the group which is anti to the OH group, and the group which is anti to this OH will always migrate in this reaction. So here you can see this OH and this methyl, they are the cis or jet type of the configuration in that case, right? And this phenyl is actually the trans or say E type of the relationship between this OH and the pH. So this pH will migrate. Okay. So how it can migrate? What I can do? So Later I'll do the mechanism as well, but right now I am telling you it is migrating in that manner, and this OH will eliminate from here. Okay, how how this OH will eliminate, I'll explain this in the form of the minus H2O. It will eliminate, and then you will have your product. Now your product would be like that: carbon, double bond nitrogen, and your pH, phenyl, which was migrated from the carbon and goes to the carbon. It is kind of 1-2 shift. Please remember, it is kind of 1-2 shift, and here this CH3 or the methyl. Okay, and of course your nitrogen. So this is the general reaction, how we can do this Beckmann reaction or the Beckmann's rearrangement. Please remember, it is very, very important. So how it had happened actually. See, you have seen that this phenyl, which was anti to this OH, right? But at the reaction, you see, it goes in the opposite direction. It is another very important feature of the reaction, right? That the group which is generally migrating, right, it always attains the anti orientation to the leaving group. So this OH was the leaving group. It will attain anti orientation to this leaving group. So I have written this pH in that manner. So this is the simple reaction. Okay, now you can see. Let's move further. Okay, stereochemistry. Now we can check the stereochemistry as well. So I'm removing it. Okay. Now you see the stereochemistry of this reaction, the point number 5. This reaction is the stereospecific in nature, as I have explained to you, right? Migrating group is anti to the OH, which I have explained. Migration origin is the carbon, and migration terminus is the nitrogen atom. It is a kind of the 1-2 shift, right? In this 1-2 shift, your group will migrate from the carbon and will join nitrogen atom after the reaction. Migrating group generally attain anti orientation with respect to the leaving group, which I have told you already. But please remember, few Beckmann's rearrangement are non-stereospecific as well. But again, I will not discuss the non-stereospecific Beckmann reactions here. I am only discussing the Beckmann reaction. Okay. And then now I think it is quite clear. Now let's do the mechanism of the reaction. How we can draw the, or how we can write the mechanism of the reaction. Okay. So let's write the mechanism. So same thing I am taking here. Say this is carbon, double bond nitrogen, okay, and this was your lone pair, and say this is your OH group, and here I have taken pH in the example as well, and I am taking CH3 here. Okay, I am doing the same reaction. So I say this is the step number 1. I can call it as step number 1, and in that case I can react this species with any of my acid. Please remember, I can use any of my acid which I have written here. So in that case I am using this PCl5. Okay, so I am doing this reaction with the PCl5. Say this PCl5 is reacting. Okay, so what will happen? It's quite easy. See, one of the Cl from here and one of the hydrogen from this OH group, this will give you minus HCl. Okay, and after minus HCl, what you will form? Carbon double bond nitrogen. Okay, this was your pH, and this is your CH3. Okay, and now this will convert into OPCl4. So what is the need of this, right? You must understand that why we have converted this OH into the OPCl4 kind of thing, or say if you react with this concentrated H2SO4, then H would go there and then it would be your OH2 positive, right? So this OH is not a better leaving group. It forms a very strong bond with the nitrogen, so it is quite reluctant to leave from this nitrogen, right? So in order to convert this leaving group into the better or the more facile or the more good leaving group, we convert this OH into the better leaving group. So that this OPCl4 is a far better leaving group of this compared to this OH. That's why we have converted it, right? So basically you can, it is a kind of the esterification reaction, guys. Please remember, it is kind of the esterification reaction. You can call it as oxime ester. Oxime ester. You can give the name to this as the oxime ester, right? I hope this is quite clear. Now the step number 2. So this was 2. Now I am going for the step number 2. Step number 2 is basically 1,2 shift. 1,2 shift. So earlier I have told you that this is your migrating origin, which is carbon, and this is your migrating terminus, which is nitrogen. So now the group will terminate, will migrate from this carbon to nitrogen. Say this is 1, this is 2. So what you can do, you can give number to this system as well. This is carbon 1, this is nitrogen 2. So this will shift, this pH will shift from 1 to 2. That's why it is the 1,2 shift. So how it will happen, you see. So this will shift onto this, and that will leave from this nitrogen atom. This is the leaving group, okay? And this is basically, you should remember, it is rate determining step as well. This is rate, this 1,2 shift is the rate determining step, okay? So what it will result actually, so it will form quite clearly CH3, then again your carbon, and then your nitrogen is also there, and I am writing the pH or the phenyl in that manner. Of course, this is your lone pair of the nitrogen, and this species is resonance stabilized. How resonance stabilization would there? This can come here. Okay, see earlier this one would be positive, right? Because carbon has lost one of the phenyl groups, so it is trivalent now, electron deficient, so it is mandatory to put the positive charge on the carbon atom. Okay. And now you can draw the resonance structure of this one. So how you can draw the resonance structure? It is quite basic thing. This is your CH3 here. This is carbon. Now the triple bond nitrogen is there. Okay. And this is your phenyl. And of course, this nitrogen will get positive charge. Yeah, this nitrogen is now become positively charged because it is tetravalent now, and the basic nature of the nitrogen is to remain trivalent, but here it is tetravalent, so we have to put this charge here, okay, this positive charge here. So this is your resonance structures, right? So this is how it had happened actually, right? So basically you see nitrogen is having the positive charge here, so it is a nitrylium ion basically. So you can call it as nitrylium ion. So I am writing it as nitrylium ion, nitrylium ion, okay? So reaction, the mechanism goes in that manner as well. Why? Because this presence of this nitrylium ion, right, it is also detected by the IR spectroscopy. So I am writing here detected by IR spectroscopy, okay? So scientists have proved the presence of the nitrylium ion with the help of the IR spectroscopy, right? It is very, very important. Now in the final step, what will happen? Say, let's move to the next page. So what will happen in the last step number 3? So you are having Me, carbon with positive double bond, nitrogen, phenyl was moved, and this was the lone pair. Now you have taken the PCl5, right? Say now I am attacking, since we will dissolve that PCl5 in the water as well, so water is also there. So now that water will react. Say this is your H2O, right, and this carbon is positively charged, so this will attack on this, okay, and when this will attack on this, you will form this particular species, Me, carbon, then oxygen, hydrogen, and hydrogen here with a positive charge only, and one lone pair only, because one of the lone pair present on the oxygen atom has been used in the formation of the bond with the carbon. That's why it will get the positive charge. This is the basic thing in the organic chemistry. Every organic chemistry student must understand the movement of the electrons when they draw the mechanism of any kind of the reaction. Okay, and then you see this was your double bond nitrogen and this is your pH. Okay, and this is the lone pair. See why I am drawing this, putting this lone pair always on the nitrogen atom. Why? See, the reason is that if you are new here or doesn't matter whether new learner of the organic chemistry or the expert, it is always important to write each and everything while drawing the mechanism. That's why I am putting all the time this lone pair on this nitrogen atom. Okay. Now in the next step, deprotonation step will occur. So here I am writing the deprotonation. I am writing deprotonation. Deprotonation. That means it will deprotonate. So how it will give out the proton from here? Let's go back. Here you can see this OPCl4 left from here. So I am having the OPCl4. So I forgot to write this. Now I am writing minus OPCl4. Okay, and that will be required in the last step. So here you can see I was having OPCl4 with a negative sign. Let's put the negative sign as well. If I forgot, right, negative sign. Why negative sign? Because this this part is moved along with this electron, right? That's why. Okay. And now this OPCl4 can deprotonate this thing. Okay. So how it will deprotonate? Negatively charged Cl will attack onto this, and this will be pushed back. Okay. And then you will have the POCl3 and one of the HCl as well. So you can write like that. Okay. So these are the byproducts. I am not interested in these byproducts, but you should know how actually it is happening. So now you will have what? Methyl carbon double bond nitrogen. pH is here. Okay, and then lone pair is here, and this is your OH group. Now basically now it is what? It is the enol form. This is alkene, that means ene part, and this is all part. Okay, this is ene, this is all, and in the tautomerism you must have learnt about the keto-enol isomerism. So this is enol form which will readily tautomerize into the keto form, and we have the method to separate this keto and the enol forms, and also driving my reaction towards the keto form. Don't worry about that. Okay. In the mechanism you should know only this thing, that it can readily tautomerize. Okay. So when it is tautomerizing, so I am writing in that manner, tautomerization. This is tautomerization. Okay, when tautomerization is happening, so what will happen in the tautomerization? Again, it is very, very important. So for tautomerization, I am explaining you how it will happen. There is a bond between oxygen and this hydrogen. So what will happen? This will shift onto this position, and that double bond will grab this proton, and when this happens, your Me or the methyl would be like that. Carbon, now it will convert into the ketone. This will become single, and your nitrogen will get hydrogen, and of course along with the pH. So here this is basically amide which is substituted on this nitrogen atom. I hope you know what is the formula of the amides. Amide is MeCONH2, right? And when we substitute one of the hydrogen of the nitrogen in the amide, then I will get the N substituted amide. So this is your product N substituted amide. Basically it is a keto form. As I already told you, we have method to shift our reaction more towards the keto form, and we have also method to separate it, right? So we'll convert this into the ketoxam. This is the mechanism of the reaction. I hope you understood the reaction well. Now one very important feature of this reaction which I have missed, now I am telling you what is the important feature. So I am writing, say for example, this is my another example, my reaction 2, okay. This is carbon double bond nitrogen, guys, okay, and say this is OH, fine, and this is your methyl, and anti to this OH, of course lone pair would be there. I will not write this lone pair now again and again. I have explained the presence of this lone pair in the pretty much detail during the mechanism of the reaction. Now I will avoid to write it again and again, but if you want then you can write it again and again for your practice, okay. Say for example, this is your hydrogen which is going below the plane, okay, and say this is your phenyl C6H5, I am writing for this one pH, right, phenyl, and this is coming up, and this is your methyl. So basically when I write this molecule in that fashion, so I am putting a star over there because this carbon is the chiral carbon. So for star I am writing because this carbon is the chiral asymmetric carbon, okay, and when it is asymmetric in nature then it must have some configuration, whether R or S. So I am telling you it is S form. This is S form. S form means the configuration of this carbon is S. See, if you don't know how to determine the R and S configuration, again I am giving you the link in the description box, whether where you can learn about the R and S configuration as well, and also the link is flashing at the right top corner, okay. So this is S form. Now what I will do in my reaction, say for example I am treating it with any of my acid, say concentrated H2SO4 I am taking in that case. You can start this reaction with any of the acid catalyst. So what will happen in that case? The product would look like in that case. See methyl. See first of all you should know how it is happening actually. So this is the OH group, and that chiral part is anti to the OH group, and when you are doing the Beckmann's rearrangement, so it will move, okay, and it will get the orientation anti to this OH as well. So what you can do, you can move onto this and this will remove from here, okay. Now I am not drawing the mechanism all the time, right. So you can write minus H2O, and then you will have your product Me. Now this carbon will convert it into the ketone. This is the basic need. After tautomerization it will convert it like in the keto form, and then you are having nitrogen. Nitrogen will get additional hydrogen as well, as I have explained in my mechanism. And now I will write this part as well, my migrated part, okay, H, and this is my phenyl, and this is your Me. So again it is a chiral center, and again it is in S form. So it has to be remember, guys, whenever your carbon carries a group which is anti to the OH and it has some stereochemistry, then this stereochemistry would be retained into the product as well. This is another example of the stereospecificity. In that case, retention of configuration is taking place. That means if you want to synthesize this S form, you cannot start with the R form. This is another explanation of the stereo specificity. You have to start with the S form in order to get the S form. If you want to the R form here, then you have to change the stereochemistry of this as well. This is the stereo specificity, retention of configuration. I am writing here, retention of configuration is the very important feature. Retention of configuration. This is very important part. I hope this is quite understandable now. Now let's see the applications, right? Another very important reactions I am going to explain. However, the length of the lecture, generally the length of my lectures are quite large, right? My lectures are bigger in size, right, in terms of the time, but they give you the more deep insight of any reaction, right? So, spend your time in the learning organic chemistry, right? Don't care about the length of the video, okay? Applications. So, first very important application I am going to explain, synthesis of your caprolactam. Synthesis of caprolactam. Caprolactam. See, caprolactams are cyclic amides. Please remember whenever I am saying that is lactam, right? This lactam means cyclic amides. Lactam means cyclic amides, right? And when you have the cyclic esters, then they are known as the lactones, right? Lactones are the cyclic esters and lactams are the cyclic amides. So how we can synthesize it? And here you can learn one very important aspect as well. That is the concept of the ring expansion. Concept of ring expansion. This is the most interesting part in this reaction, right? So how we can start this reaction? Say for example, I am having this starting material, this 6-membered ring. Please focus here. It is very important. This is double bond nitrogen, and here I am having my OH group, and of course this part will have the lone pair. So earlier in the earlier two examples, I have taken the starting material where you don't have any cycle. Now I have introduced that kind of your oxime, keto-oxime, where you have the cyclic part, right? That means migration would be little bit difficult to understand for the beginners, but I'll make everything clear in this lecture. So it is very important that you must focus how I am doing the reaction. So I am taking, in that case, say again PCl5 I am taken. I am not going into the mechanism. Now you know your HCl will remove from here and your OPCl from here actually, okay? Not yes, OPCl4 negative, right? This will remove from here, and then okay, so what I am doing, I am not removing OPCl4, I will remove this in the next part so that you can have the better understanding, okay? So this is nitrogen here, and this will convert into what? OPCl4, right? And HCl has removed from here, one of the H from here and one of the Cl from here, minus HCl it will remove. Now you left with the PCl4, this will connect here. Now in this step, it is very important to give the number to the system in order to expand the ring. Say this is carbon number 1, this is carbon 2, this is 3, this is 4, this is 5, and this is 6, right? So it's a 6-membered ring. Now you see, you know, this OH group is having here, and that carbon, which is carbon number 6, it has the anti-orientation to this OH group. So this group will migrate, not this one, because this has this carbon 1 and 2 is having the cis relationship, cis relationship to this leaving group. But you know, in the Beckmann's rearrangement, always the group which has anti-relation to this leaving group will migrate. So this will migrate, okay? So what will happen in the next step? This bond will break from this bond breaks from here, and it will shift onto the nitrogen atom. Please remember, migration origin is the nitrogen and terminus is the migration origin is the carbon and migration terminus is the nitrogen. So carbon will migrate from here, position 1, to the nitrogen atom, and this will eliminate, okay? So what will happen in that case? You see, OPCl4 negative will eliminate. Now you have the 7-membered ring. Earlier you are having the 6-membered ring here. Now this nitrogen will also sit or will also join this ring. So it will become a 7-membered ring, and carbon 6, in between carbon 6 and carbon 1, you will have the nitrogen. Carbon 6 and carbon 1, you will have the nitrogen. So let's make a 7-membered ring first. Don't care about the position of the nitrogen. First you will make this 7-membered ring. So write 7-membered ring, and you can number it, this 7-membered ring, in that manner. Say this is carbon 1, this is carbon 2, this is carbon 3, 4, 5, 6, and say this is 7, right? And you know, in between carbon 1 and carbon 6 you will have the nitrogen. So this is carbon 1 and carbon 6. In between this you will have the nitrogen, so you will write nitrogen over there. And that nitrogen is also having the double bond between carbon and nitrogen. Carbon 1 and nitrogen, you will have the double bond as well. So you will write the double bond here. In that manner you will write. Okay. And of course, lone pair would be there. And now you can see here, since this bond has broken from here and it has shifted here, that means your carbon number 1 has lost its bond. That means it is now trivalent. It is now trivalent. When it is trivalent, then you have to put positive charge here. So it is kind of nitrillium ion, cyclic nitrillium ion. So I am writing here cyclic nitrillium ion, right? I hope this is quite clear now. Very important. Now remaining part is quite simple. You will use water molecule, that is H2O. Okay, this will attack onto this carbon number 1, and then you will have your next species, again a 7-membered ring, like that only. Nitrogen is here with double bond. Okay, and now it will have what? O, H and H with positive charge, because one of the lone pair of the oxygen has been used in the formation of the bond with the carbon. Okay, and now it is, since it is tetravalent, it is at substitution, so this positive charge will shift from carbon, from this carbon to this oxygen. I hope this is quite clear. Now in the last step, what you will do, you will have this species which you have removed from here, O PCl4 negative. So you can write your O PCl4 negative. This will grab one of the hydrogen, it will push back the electron pair onto this nitrogen atom. So you will have again what? HCl and POCl3, like that. Okay, and then you are having then you will have your enol form. This is your 7-membered ring, guys. Nitrogen is here. Okay, this is double bond, and this is your OH. This is enol form, and that enol form will readily tautomerize. So I am writing tautomerize. Okay, how the tautomerization will occur? The bond which is present between the carbon and the oxygen and the hydrogen, it will shift onto this position. Okay, and this will come here and finally grab this hydrogen, and then you will have your product, which is the keto form. This is nitrogen. Now along with the hydrogen, this will become single, right? So, and this will now double bond oxygen, right? So this, because it is shifted here, so it will get a double bond. This had shifted onto this nitrogen atom, we finally will that will finally grab this hydrogen. So this is where cyclic amide basically are the lactams, and the name of this compound is the caprolactam. Caprolactam. So you have increased the size of the ring from the 6-membered to the 7-membered. That's why it is the very important example of the ring expansion as well. And you know, this caprolactam is very important starting material in the synthesis of nylon 6. Very important starting material for the nylon 6. It is a very important application. So how you can get this nylon? It is again very simple. what you can do, you can react with say concentrated NaOH or aqueous solution of the NaOH, right? And if you heat this mixture, you know, this is the acid derivative, it will react with the OH. So what will happen? The bond will break and you will get your compound. So how the bond will break from here, I am telling you, right? So here you can see in the caprolactam, in this part, this bond will break, any of the bond, right? So I am breaking, say for example, this bond, okay? So now you have say 1, 2, 3, 4, 5, 6 and 7 is the nitrogen. So it is, this numbering is not according to the IUPAC, but you have broken this particular bond. So what will form? NH, I am writing NH here, this NH part, and then it is, sorry, not this bond, not this bond, I'll break this bond. This bond will break. This linkage is quite weaker one, right? This linkage is not, see please remember, this 1,7 bond is not weaker, this 7,6 bond is quite weaker, so I will break this particular bond. So when this bond will break, okay, so I will get my NH here and it is connected with the carbonyl part, and then the remaining 1, 2, 3, 4, 5 carbon atoms, right? So 5 carbon atoms I am writing CH2 5 times. So this is my polymer. So this bond will continue from here to here and here to here. So this is nylon 6. Nylon 6. Okay. So this is how you can synthesize this. Nylon 6 you can synthesize. Very important starting material. Now you can take different examples. Say for example, another heterocyclic will form in that case. Synthesis of piperidone, okay, and more specifically 2-piperidone. Piperidone. Now we will synthesize this. Again, this is the very beautiful example of the ring expansion. Say this is my 5-membered ring, okay, where this nitrogen will attach to this OH. This is another keto-oxime. Now this time I am reacting this with H positive. So one of the lone pair present on the oxygen atom will grab that hydrogen. Okay, now I am doing very quickly. So this is double bond, this is nitrogen, this is OH2 positive. If you number it, say if you want to give number, right, this is 1, this is 2, this is 3, this is 4, this is 5, right? And this group will migrate because it is this carbon 4 and 5, this linkage between 4 and 5 has the anti relation with this leaving group, so it will migrate and this will remove from here, minus H2O. So now from 5-membered ring you will have 6-membered ring, okay. So straightforward write 6-membered ring and say this is carbon 1, this is carbon 2, this is 3, this is 4 and this is 5, okay. So between, since this has, so okay, please let me remove this. Let me remove this, okay. Okay. Now 6-membered ring I will make, or did I make any mistake? Let me check. Okay. Now you see this bond has migrated. That means carbon 4 and carbon 5. You see carbon 4 and carbon 5, in between carbon 4 and carbon 5 we will have the nitrogen atom. We will have the nitrogen atom, carbon 4 and carbon 5, okay. So suppose I am writing this in that manner. I'm making this carbon S4, this is S5. So this is 3, this is 2, this is 1, and in the center I'll put nitrogen here, okay. And that nitrogen will form a double bond, okay, and that will connect it with this carbon 5, okay. When I do this, then definitely this carbon 5 will get the positive charge, and when I'll react with this water, it will come here and it will form this nitrogen double bond. This is my OH2 with positive charge. Now I am doing the deprotonation, minus H positive. I am not drawing the mechanism, complete mechanism. So when the deprotonation will occur, so this will shift here, and then you will have here this compound, nitrogen in the center, double bond, and this is OH. This is enol form, which will readily tautomerize to give you the keto form. Nitrogen will get hydrogen and this will get double bond. So this compound is your piperidone, 2-piperidone. Now this is very important. And my last example, where see in the first slide, if I go back in this particular slide, I have written what about aldooxime. So I am taking the synthesis of the isoquinoline, okay, to explain the reaction of aldooxime, which undergoes your Beckmann's rearrangement. So I am writing synthesis of isoquinoline. Synthesis of isoquinoline. Okay. So I'm see how the actually reaction goes. So for example, I am having cinnamoldehyde, right? This is CH. This is double bond CH, cinnamoldehyde, right? Why the common name of this compound is cinnamoldehyde? If you have any idea, see if you have any idea why the name of this compound is, common name is the cinnamoldehyde, please comment in the comment section, right? Later I'll give you the answer if you don't find, okay? So I can react this with hydroxylamine, which is your NH2OH, normal condensation reaction will occur. That means minus H2O, right? So how I can eliminate? This is my oxygen, and these are the two of the hydrogen, again a condensation kind of the reaction, okay. And then you see here, right, this is CH, this is double bond CH, this is single bond CH, double bond NOH. So this compound is basically your cinnamoldeoxime. You can call it as cinnamoldeoximes. So I can, if you want, then I can write here cinnamoldeoxime. That means oxime of the aldehyde. Now it is quite important, quite easy rather, right? I'll react with this concentrated H2SO4, so that oxygen will grab it, and then you will have the better leaving group when your OH is protonated. This is CH, double bond CH, single bond CH, right? And this is double bond N, and say for the simplicity I am putting my OH here, giving anti-relationship, okay? And this is OH2 now, it is positively charged. It is a better leaving group. Now you know this is OH, and after this double bond, that entire part, this entire part, so I am circling it, entire part, this is basically your leaving, this migrating group, right? Say this is carbon 1, this is nitrogen 2, 1 to shift you will do here. So that group will migrate from here to here, and this will eliminate from here, and then you are having minus H2O, no problem in that. And Then you are having this thing, since this has migrated. So what you can do, you can write it as CH double bond nitrogen. Okay, now this will come here, which is your connected with this CH, right, and double bond and another CH. This is how you can make it. Now this carbon is positively charged because it is trivalent, right? See, always please remember from where actually, from carbon from where actually the group is migrating, it will always get a positive charge. So positive charge is here. So for simplicity I can write this is 1, this is 2. Now this is 3 and this is 4. There is no problem in that. Okay. So this is how you can form it. There is no problem in that. Now what you will do, you will protonate this. That means addition of water, not protonate, sorry, addition of water. So this will attack on this carbon number 1. And when this will attack on the carbon number 1, so you will have this species CH, oxygen, hydrogen and hydrogen, positive charge on the oxygen, right? Double bond nitrogen and then your CH and again your CH, and that is connected with the, phenyl ring as well. And let's delete this part, this will confuse you. Okay, and in the final step what will happen, I'll deprotonate this, that means minus H positive. Okay, so this will remove from here and then you will have the enol form. So in the next part I'll make this, I'll write this enol form for this. Say this is CH and this is double bond nitrogen. Since it is a enol form, so it will OH now, no problem in that. And this is your CH, double bond CH, and that will have this system, no problem in that, right? And now you can see here, if I give number to the system, right, if I give number to the system, so this is 1, this is 2, this is 3, this is 4, okay, and you know at this position you are having hidden hydrogen on this of this benzene. So what will happen, these two can react very easily since they have the very close vicinity, right? And then what will happen, ring closure will occur. Earlier ring expansion was there, here the ring will close, minus H2O. So now you will form a new 6-membered ring, 1, 2, 3, 4, and let's call it as carbon 5 and this has carbon 6. So what you will have in that case, see this ring was already there, that part. Now if you put CH here, so you will make another 6-membered ring, CH here, this CH, and this is double bonds, this is single bond, this is again double bond, alternate single and the double bond. This you are actually getting, okay. So this, this and this, okay. And you see here, if you number it, right, again for the simplicity, what I can do, I can number it. Say this is 1, this is 2, this is 3, this is 4 and this is 5, this is 6. And now you can see here carbon 1 and 2 is having the double bond. So you can straightforward put double bond between carbon 1 and 2. Similarly, your nitrogen 3 and your carbon 4 is also having the double bond. So at position number 3 you will write nitrogen and double bond between the two. So basically this compound is your isoquinoline. This compound is isoquinoline, right? So you, if you want, then you can make it rather more correctly. this part, okay, and here you see double bond at this part and at this part, okay, and then you are having nitrogen in between the two. So here I am putting my nitrogen here. So this is your isoquinoline. Okay, so this is how you can synthesize this isoquinoline as well. This is another very important example. So see, there are various kinds of the reactions. Another very important part is the determination. See, another very important application, which is the last application, determination of the configuration of the oxime. Determination of the configuration of oximes. Okay. So how we can determine the configuration of the oximes? Okay. So let's take the example. So how we can actually determine the configuration. Say, for example, you are having this species. Carbon double bond nitrogen, okay, and this is your OH, and say my C6H5 phenyl is there and my CH3 is here. So we will do the Beckmann's rearrangement. So I am writing Br for the Beckmann's rearrangement, and I know I will convert it into the oxime. That would be your CH3, carbon double bond oxygen, and then your nitrogen H, okay, and of course my phenyl part, okay. This is the example. Now I will hydrolyze it. I will do the hydrolysis for this one. Hydrolysis. That means I will take the water, OH negative, H positive, okay. So when you hydrolyze it, what will happen here? You know, this nitrogen is having lone pair. This will grab the hydrogen. That means you will have NH2, and then remaining part is your acid, CH3, C double bond O, OH. See, when you do the hydrolysis of your N substituted amides, you will always get the amines and your acid. So here you can see this amine part is having the phenyl group. That means that phenyl must had or anti-relationship with that OH group. Please remember, whenever you hydrolyze any keto-oxime, any N substituted amide, right? When you hydrolyze it, then your amine and acid will result. Amine part, the amine which the alkyl group which is there, which is present on this nitrogen atom in the amine, that must have the anti-configuration or the anti-relation to the leaving group. So it is now, say for example, say for example, I have started reaction, this reaction in that manner. CH3, C6H5, C double bond ON, and then OH. If I do the reaction in that manner, finally I will get this one. Here in that case, I don't have any idea about the configuration, but when I'll get this product after hydrolysis, then that amine part with this amine which is having this alkyl group, this must have the anti-relationship, because this has migrated onto this nitrogen atom. You know, this has migrated onto the nitrogen atom and this is forming the amine. That's why this reaction is of particularly importance, right, when you determine the configuration of the oximes, right. More specifically, when your Beckmann's rearrangement is the stereospecific type, but some examples we have of non-stereospecific. In that case, it will not actually do the needful thing. So it is up to the students. Be careful whenever you are doing the stereospecific. Whenever you are doing the stereospecific or your non-stereospecific Beckmann's rearrangement. In case of the stereospecific Beckmann's rearrangement, amine part will always have the alkyl group which earlier had the anti-relationship to the OH group, but if it is non-stereospecific, then this will not work. Okay. So I hope you understood the reaction well. So there are many things about this Beckmann's rearrangement, but for CSIR, NET, GATE, JEE and various other examinations, this much of information will be quite useful. I am not saying that this is all, right? Nothing is all actually. You always need to prepare more and more in the particular kind of the reactions or the concept actually, right? But this will give you the more deep insight of the Beckmann's rearrangement. Okay. So I hope you like the lecture. If you like the lecture, please like the video and share tetrahedron chemistry classes with your friends as well. I'll meet you in my next class. Okay. So that's it for today. Thank you. Thank you very much.